All right, good morning, ladies and gents. Today I am out sick, so please, if you guys have any questions, shoot me an email or message through Remind, and I will get back to you guys if there's anything you guys need. Couple things for today. Number one, don't forget Freshman Focus. We are every single class down in the media center, not the media center, down in the cafeteria. The media center is closed though, so please don't be going to the media center. They're going to be doing testing in there all week. I believe it goes into next week as well. So please make sure just head down to the cafeteria and check in with your teacher. Today during class, you guys are going to be watching this video. Please make sure you do watch it as I'm going back over everything that we talked about last week leading up to Thanksgiving break. If you missed a day, you'll be fine. Still watch the video, and that will catch you up on what you had missed. Then you guys have a small quiz to take. You do have one attempt. You only have one attempt, okay? So please make sure don't submit it until you're like, I got it, I'm good. You can use your notes. I'm going to let you guys use your notes on this one. It'll be open note. And then big thing, it's due tonight, 11:59 p.m. All right, so we originally talked about two forces that impacted the stability of our nucleus. We had the electromagnetic force, which is our opposites attract, likes repel. We know within the nucleus there are protons and neutrons. So since the protons both are positively charged, whenever they are close to each other, if we put a positive by a positive, they're not going to want to hang out by each other. They're going to move away from each other. So that causes the nuclei to be unstable. If there is a force that's going to try to force apart a nucleus, in order for a nucleus to actually exist, there must be a force pushing it back together. And that force is the strong nuclear force. This is the attractive force between our protons and neutrons. It ends up making for a very stable nuclei. So between these two forces, if I have the electromagnetic force being greater than the strong nuclear force, then decay is going to occur. We do have a couple different types of decay that occur that I'm going to be showing you here in a second. If the strong nuclear force, though, is stronger than the electromagnetic, then that makes it stable. So why it might be unstable is either because maybe it has too many protons, and our maximum number of protons for it to be stable would be roughly 82. So anything with 83 or more is going to be too many. There's going to be too much positivity in that really, really small, tight space. There's going to be too few neutrons. Or just in general, remember I said if the electromagnetic force is greater than the strong nuclear force, that will cause it to go through a decay process as well. Okay, so the types of decay that we might have, you could have alpha, beta, gamma, or neutron emission. Alpha, we would lose 2 protons, 2 neutrons. That's going to cause the mass to go down by 4, so ultimately it's going to give me a smaller nuclei. Beta is going to be the loss of an electron. Gamma is the emission of light. So remember, light does not have mass, it does not matter, but that usually accompanies alpha or beta decay. Neutron emission, obviously with the name, we're losing some neutrons. Okay, so our atoms, if it is unstable, if it has some of those characteristics that I had mentioned, like too many protons, too few neutrons, or if that electromagnetic force is just a little bit too strong, then the atoms are going to go through a decay process. And they will decay and decay until they become stable. So they could go through many processes of decay. If I have an unstable parent nuclei, that's going to decay into a stable daughter nuclei. So remember, no mass is getting destroyed here. We're not losing any matter or anything like that. It's just going to ultimately get transformed into a more stable version of the isotope. So if we understand the process of decay, we can actually use the process of decay to predict how old things are. So we have relative dating versus radioactive dating. Relative dating is saying that you, the student, are younger than me, but then your parents are older than me. Okay, so relative dating, that's pretty good. That doesn't really tell you anything about age. Whereas you guys know you're about 15, I just turned 30, and most of your parents maybe are like, I don't know, we'll guesstimate 35 to 45-ish, maybe, somewhere in that range. So relative dating doesn't tell me exact ages, but it just tells me that I am older than you. Whereas radioactive dating, a lot better, you've probably heard of this as carbon dating, is going to be able to give me an age of a material. So for our fossils, this is how we know how old the dinosaurs are. This is how we can try to get a pretty good idea of how old the universe is, how old our solar system is, how old our Earth is. That would be with radioactive dating. So we use this concept of half-life. Half-life is a set amount of time it takes for a certain isotope of an element to decay. Each isotope is going to decay at different rates. And so when we're able to determine their half-life, then we can look at what percent of that radioactive material remains in a sample, and then kind of work backwards from there to get age. So half-life, we had spent a day looking at half-life and doing some practice problems with that. So on this first one, if I look at this one, it says if 6.25% of a radioactive element remains, how much or how old is the fossil if each half-life is 5,000 years? Well, because it's asking for a percent and it gives you a percentage, you always want to start at 100%. Because at time 0, none of it has decayed. And then take a half of that. So half of 100 is 50. Then take half of 50 is 25. Take half of 25 is 12.5. And then go ahead and take one more half and do 6.25. So I finally got to that final percent that was mentioned in the problem. Now if I had asked you how many half-lives have occurred, there's 4 arrows. I divided it by 2, or I took 1/2 of the sample 4 times. Well, each time I took that half, that took 5,000 years. That's what's given to me, that it's half-life. So above each arrow or below each arrow, I'm going to go ahead and write 5,000 years. And then if I add all those up, that'll be 20,000 years total. So this sample would be 20,000 years old. For the next one, it says if 1/8 of a sample remains. Well, since it's giving me a fraction, I'm always going to start out as 1. So I'm going to start out with 1. Half of 1 is 1/2. So that's 1 half-life. Half of that half then is 1/4. That's another half-life. Half of that is 1/8. So you just continue to take 1/2, 1/2, 1/2. So to go from 1, take half of that is 1/2. Half of a half is 1/4. Half of a 1/4 is 1/8. Okay. So then if I count up my number of arrows, I've had 3 arrows. That represents 3 half-lives. So I could say, all right, well, how old is the sample? If I told you that the half-life is 10 years, then you go 10 plus 10 plus 10, which would give me 30 years old. Or I could tell you that the sample is 75 years old. How long is each half-life? Well, since it's been 3 half-lives, 3 half-lives took 75 years. 75 divided by 3 would give me 25. So lots of different ways for me to ask you those questions. On our half-life graphs, we graph something very, very similar to this on, Friday, even before Thanksgiving week, when we did our M&M's lab. If I started out with 1,600 candies or 1,600 atoms that have not decayed, half of that would be 8,000. And then if I look at that graph, it took a total of 8 days for me to reach 8,000 candies, which means in another 8 days, which would be a total of 16 days, I should be half of the 8,000, which I am. I'm at 4,000. So remember, on a half-life graph, it's going to look like that. It's going to be exponential decay. It's going to get really, really close to the 0, but it is not going to actually hit 0 because it's not possible for us to keep dividing it by a half and hit 0. All right, we had mentioned then the following week, we had talked a little bit about atomic bombs, and we said, how do we use nuclear energy? What are the good uses for it? What are some of the not positive uses for it? So we had mentioned the equation E equals mc squared. This is Albert Einstein's equation. And that is the energy released is going to be equal to the mass times the speed of light constant, which is squared. The speed of light constant, this is a big number, 3 times 10 to the 8th. And then I need to square that value. So even if I have a small amount of mass, I'm going to be releasing a lot of energy. So this can be used in a positive way, right? In order to create a lot of energy for our communities. This would be a better alternative to using fossil fuels, which we use right now. So we use coal and we burn it. So that's not a good form of energy. Nuclear is a lot better. We do have 2 nuclear power plants here in Ohio, both along Lake Erie, or it can be used in defense in the form of nuclear bombs. Remember, I had mentioned the U.S. were the only ones to have ever used nuclear bombs against another country. We used it against Japan in World War II. So again, if we're releasing a lot of energy, then it just makes a bigger and more destructive bomb than a regular typical type of bomb. So in terms of the nuclear weapon, that just related to more death and more destruction in Japan during World War II. All right, so the 2 types of technology then, we have fusion and we have fission. We can do one of them, we cannot do the other. Fusion, we cannot do. This is the process that takes place on stars. This is when we combine 2 smaller nuclei. So combining of 2 smaller ones like hydrogen and hydrogen. I'm going to combine it to make a bigger nuclei. Okay, we do not have that technology right now. If we could do this, we would produce helium, which is not a horrible thing. We could just fill up a lot more balloons, which wouldn't be so horrible. Fission would be the splitting of a large nuclei into 2 smaller ones. In order to split those atoms, the United States used uranium and plutonium in the 2 atomic bombs. They shot neutrons at it, and that caused it to split and started a chain reaction. So when you take that large nuclei and you split it, that's going to release a lot of energy. This is the process that we have right now. We can do this. The only thing with this, though, we do create that radioactive waste, which is not a great thing. Remember I had mentioned saying that they actually dig holes in the side of a mountain and kind of take that radioactive waste and stick it in there and then cover it back up. Not the greatest solution, but hopefully we will find a way to actually do fusion one day, which would be a lot better. All right, so don't forget, after this video, you have a quiz to take. Okay, just watching this video, you should be good to go on the quiz. You do get access to your notes or to the internet if you need it. It is due tonight. Okay, please remember, due tonight, 11:59 p.m. So do it right now in class. Don't worry about it. Get it done, and then you have nothing to do tonight. Don't forget, submit anything. If you missed a couple days, please make sure you look at the lab. There's a lab. I gave you data. Please take a look at that. And then don't forget, 8th period, you are in the cafeteria for focus. Okay? No library. It's closed today. All right. You guys have a great day.